Good afternoon, everybody. Welcome to this new DinAmicI online seminar. We are happy today to introduce our first speaker, which is Lai-Sang Young from the Courant Institute, Mathematical Science, DinAmicI of the New York University. And she will talk about dynamics of the visual system.
Should I start?
Yeah, please. Thanks.
Okay, so hello everyone, and thank you for having me. As some of you probably know, I've been playing with dynamics of the brain for the last about 15 years, and I want to convince you that it's a really interesting dynamical system. But instead of talking about it in the abstract, I want to show you a little piece of the story to give you a flavor of what it's like. Okay, so the story today comes from the visual system, which is what I have been working on. And so there are two basic properties of visual neurons that I want to focus on. One is called orientation selectivity, abbreviated OS in this talk, and it's used in the detection of edges. Like how do you see this edge over there, the edge of the sun, and so on. And the other one is called direction selectivity, abbreviated as DS. So OS and DS are the two properties, excuse me, that I'll be talking about in this talk. Well, maybe I should say a little bit more about DS, which is implicated in pursuit eye movements. So what are pursuit eye movements is that when there's a moving object in your view and you try to track it with your eyes, okay? So now our visual angle is actually very wide, so we can see a very wide swath of the space in front of us, but there's only a very small region corresponding to the fovea in your retina or center of gaze where the acuity is the strongest. So when you try to track an object, you always try to put your strongest point where the object is. But by the time you put it there, the object has moved here, okay? And if you then start to look for, oh, where is it? And then you find it here, it's too late because it's again moved on. Okay. So what we need is the ability to anticipate the direction of movement. Okay. And this ability to anticipate the direction of movement is called direction selectivity. So these are the two properties that I'm going to talk about throughout the whole talk. Okay. So what is the problem? The problem is that when visual signal enters your eyes, it goes to the back of your retina. Okay. And from there, your optic nerve takes it directly to this little structure called the lateral geniculate nucleus. It's a little peanut-sized structure called lateral geniculate nucleus because it kind of looks like the shape of a knee. Okay. And so it's just your optic nerve takes you directly from there to here. And from there, in one synapse, it goes to the visual cortex. It goes to the first processing stage of the visual cortex, which is V1, the primary visual cortex V1. So it goes from the visual field to the retina, from retina to LGN, and from LGN goes to now the V1 is complicated. V1 is complicated, it's got many layers. Okay, we're only talking about the input layer, so one layer of V1, and there's actually even two input layers. We're talking about the Magno pathway, so one of the two pathways into V1, the input layer. So my talk will be mostly about this part. So what is the problem? Is that here are the experimental facts. LGN has cells, has neurons, and you look at the cells in LGN, they are unable to detect orientation selectivity. So they cannot tell edges at all. And they cannot tell orientation, they cannot tell directions, they have no direction selectivity. And yet, and there's nothing between these two, but by the time you get here, most of the neurons have OS and about half have DS. Okay, so the question is, how did that happen? What is the origin of these two properties? Okay, so this is a question I'm gonna try to explain the answer to. And okay,
sorry, just to understand
yeah.
this experimental fact, what does it mean? That they looked at the neuron
They
to
look at the
see
cells
if they
there.
fire.
Yeah. They look at the so go back, okay. So they look at the cells, okay, and they present something with edges with or gratings, drifting gratings, and from one direction and from another direction, the cell behaves exactly the same way.
I see.
Okay, so it doesn't prefer a direction, it doesn't prefer an orientation at all. But then you go to here, and you do the exact same measurement, and they definitely have a very definite preference. Okay, so the question is, where did that come from? Okay, and so that's going to be the story. Okay, so just repeating the same picture. Yeah. So now the retina is very complicated. I'm not going to talk about this because that in itself is like a like a big thing that some people you can study this whole part for a very, very long time. Yeah, but I'm going to skip over it, but I don't want you to think that it's because I think it's unimportant. It's just that I don't want to talk about it, except for two things. One thing is that the cells in the retinas have very small receptive fields, meaning receptive field means that if you look at a neuron, it's sensitive to only a very small region in your visual space. For each neuron, it's sensitive to a very small region in the visual space. That is called its receptive field. Okay. And if you look at the receptive fields of all the neurons, okay, they kind of tile the whole visual space. Now, of course, I don't mean tiling in the rigorous sense of mathematics. Right? These visual fields are they're overlapping, but they're not overlapping too much. They more or less kind of fill up with some overlaps the visual space. Now, I'm lying here at one point. There's one place near the fovea when they really pile up. Okay, things are very complicated. Mathematically, the fovea behaves like a singularity, and nobody knows very much about it. So I'm going to stay away from the fovea a little bit, okay, to regions that people have much more better control. So you imagine that it's mostly at the back of this whole area of the retina is filled with little regions of receptive fields that are overlapping, but not tremendously so. This means that there is a mapping from your visual field to the retina. So it's a picture. It's 2D. Visual field is 2D. So there's a mapping from this 2D space, kind of position by position, to the 2D space at the back of your retina. Okay, think of it as like homeomorphism or something like that. Of course, it's not. Right? Okay. Now the important thing is that this retinotopic map passes to LGN, which is also roughly two-dimensional, and then to the layer of V1, which is also roughly two-dimensional. Okay, so in other words, there's like a coordinate mapping from your visual field to the back of your retina to the two-dimensional network here that I'm going to talk about to another two-dimensional network here that we're going to talk about. Okay, so it's like there, meaning that there's a point here corresponds to a point here, corresponds to a point here, correspond to a little region in the visual field, and it's like a homeomorphism, continuous change of coordinates. Okay, so this is kind of the background. So what I'm going to do is that I'm going to skip over the retina in this talk. I'm going to go directly from the visual field to LGN and to V1, and I will first talk about the dynamics of LGN, followed by the dynamics of V1, and then after that, this is kind of background, and after that, I will go to a proposed mechanism that will explain why we see edges in here but not in here, and a proposed mechanism for direction selectivity. Okay, so okay, LGN, structure and dynamics of LGN. Okay, LGN has many layers, so I'm talking about one layer that in this one particular pathway. So I mean, I'm just talking about one layer of LGN, one layer of cortex, because that's kind of complicated enough for me. Okay, so LGN has two types of cells, on cells and off cells. The on cells are excited, so each cell sees, of course, it doesn't see anything, but it's sensitive to a little tiny region in your visual field. And this on cell gets excited when in this little area that it sees, it changes from dark to light. And off cell, they are excited when it goes from light to dark. Okay, so basically they sense the changes in luminance. The two kinds of cells are sensitive to two kinds of changes. Okay, so I will show that to you more precisely in a moment. And the second fact is that it's very sparse. There are very few of these cells. And if I tell you how sparse, it may scare you. It's that if you hold out your arm like this and look at your thumbnail, that region corresponds to about 10 of these cells, 5 on and 5 off. So does that make you nervous that what if you, they shout that all the time, right? So what if you lose a few of them or something like that? Okay, don't worry, it's okay. So you'll make up for it some other way. Okay, but it's very sparse. Okay, there are really very few of these cells around. Okay, so more precisely, this is of course a model. There's no but this is a very standard accepted model. So showing you again that I'm talking about this part. Okay, the input current to LGN is basically like this. There's a light intensity map so this pathway doesn't see color, so it's only luminance, it's only light and dark. Okay, so this is light intensity map, meaning that at X location X, okay, we know what location means because we have this coordinate system at time T or T minus S here rather, okay, how light or dark this is. So this is a light intensity map. And you convolve that with a temporal kernel and with a spatial kernel. Okay? And then, well, a little bit more than that, there's some background stuff going on, and you have to take the positive part and so on. But basically, it's light intensity convolved with spatial, convolved with temporal, and that's what LGN, the input to LGN does.
But
and I
what
put
is
n
XK? XK, what is it? XK? I don't understand this.
XK.
Yeah, XK.
Oh yeah, I'm going to show you.
minus-
These are kernels. This is the spatial kernel, and this is a temporal kernel. So actually, I should show you right away. Okay, the spatial kernel is, it just looks mostly like a Gaussian. Actually, not a Gaussian. It's the difference of two Gaussians, but don't worry about it. Basically, you just take a little area and you sum up the stuff, right? Like you do a Gaussian. This is the part that's interesting. This is a funny thing to convolve with. You're convolving with something that looks like a sinusoid. Okay, so what it means when you convolve with a Gaussian or a little disk and indicator function, a little disk or something like that, is that you average, right? That's what we're used to. Convolving with something like this means that you are taking derivatives, basically, right? You're taking something minus something. So it's the temporal kernel when you convolve with it is roughly like you are looking at the situation roughly 30 milliseconds earlier, subtracted minus that situation. So that's how you detect change, right? You convolve with something that's like taking a derivative without letting the denominator go to zero, right? It's always about 30 milliseconds. Okay, so when convolving with this thing, this is how you get light to dark and dark to light, depending on the sign here. Okay, so
sorry, but still I'm confused because this.
Yep.
I mean, this is a convolution, but it is the distance of X from some point XK, which I don't understand what it represents. Is that the neuron?
Yeah. Somebody had it's a convolution. Okay, just say
Okay, fine.
just click from another paper.
Okay. But then I will
Okay.
depend also on X. It's not just a function of T. It's also a function of
It's
X and
both a
T.
function of X and of T. So
Okay,
X is
fine.
the
Then I
spatial
understand.
is the
Okay,
spatial
thanks.
kernel. Just think
Okay,
of that
fine.
as more or less summing over a little area, but
Okay.
with the more in the middle to the side. Okay. The K is the K. So in this paper, somehow K is written different than the X here because it's put in there. Sorry about that. I just clipped it from a paper. Okay. So, but this one is like you're taking a derivative in time. Summing in space, taking derivative in time. Okay. So, and this is why you are detecting the changes from light to dark and dark to light, depending on the sign of them. It's upside down for the other one. So, this is all there is to know for this talk about what LGN does. Right? Ready to go to the next one? Okay. Okay. So for this is one layer. This is just one layer of V1. All the layers are kind of similar, but not the same. Okay. Now I call it, whenever I put a quotation here, it means that I've taken some kind of poetic license to turn it into mathematics, and it's really not exactly like that, right? So this network it is a network. Okay, it's much more 2D than 3D. Okay, it's got a very thin layer but very big. So mathematically, the model is a 2D network. Okay, And of course, there's no such thing as completely translationally invariant. But what I mean is that if you look at one spot and you look around you, the architecture looks very similar to if you look at another point. Mathematically, that's got a very quick way to say it, right? So I give you a little bit of a sense of, you don't have to know exactly these things, but just to give you a sense of what it looks like. So we have to study this thing, we've divided it into about 7 to 10,000 regions of this network called hypercolumns, representing distinct receptive fields. There is no such thing. The receptive fields changes gradually from one to another. But, when we talk about it, it's really easy to just cut it up so that we have a way to talk about it easily. And the receptive fields change in size. So at the 5 degrees from the fovea, like your center of grace, you move to the side a little bit by 5 degrees. It's roughly half a degree by half a degree for each receptive field, which is like the size of the moon when you look up at moon. Okay, so this is kind of how much each region kind of represents, and each one of these regions has about 4,000 neurons per layer, and about 80% of them are excitatory and 20% inhibitory. So I think everybody knows what excitatory means, right? When you fire, you excite everybody, and when you inhibitory means you inhibit everybody. And the connection probabilities between neurons, okay, is modeled usually as truncated Gaussians. Okay, so again, quotation in green means I'm kind of lying a bit, turning it into math. Okay, now in this layer is easy to study because there's no long range connections. In other layers, there are long range connections. So this layer is particularly easy. Okay, so let me just draw it for you like this. So if I think of this as one hypercolumn, okay, it's kind of like a construct that we make up in our head, right? It's not, okay? And if you take a neuron and E cell, and if you look at all the cells that send signals to it, that are presynaptic to it, the E cells, there's like a couple hundred of them, and they are kind of spread out roughly to this extent. These things are actually anatomically about this far. Okay, and this is about 0.5 of a millimeter. So I cells get more E input, okay, and E cells have a shorter range. So if you take any cell, blue is I in this talk, right? So you get the input from the local I cells. So this is the network kind of each square has about 4,000 cells. Each dot here is a cell, and each one gets input from this many, and this is what the network looks like. Okay, so a lot more cells than LGN. Okay, and what about the equations of neuronal dynamics? Well, each neuron, there are many models of dynamics of neurons. Hodgkin-Huxley is perhaps one of the more elaborate ones that describes kind of more carefully how an action potential is generated. But let me just talk about one, which is kind of good for my purposes, is the leaky integrate and fire equation. Okay, so the leaky integrate and fire equation basically says I'm only going to keep track of the electrical properties. I'm going to forget about all the zillions of biochemical processes that's going on. So the only thing I keep track of is the membrane potential of a neuron. So a neuron has a membrane. The inside and the outside, the charge is different. So there's a membrane potential. And the changes in membrane potential governs the firing, roughly like this. So dV dt is governed by 3 terms. Okay, if nothing happens, it gets let's talk about this in a second. So these are actually from like minus 70 millivolts to minus 55 millivolts or something like that, but it's been normalized to 0 and 1. That's in the math model. So most of the time is in this region. And when it reaches 1, which is the spiking threshold, it fires a spike and it gets reset to 0. So it just oscillates here, anytime it reaches 1, it will fire a spike and then it will get reset to 0 and starts again. So the membrane potential is governed by 3 terms. One is the leak term. So if nothing else is happening, it will just go back down to the 0. Okay, so and this term, which is the excitatory current, tries to drive it towards some imaginary point up here that it never gets to, because by the time it reaches 1, it already fires a spike and it resets. But still, the force is to push it towards some point, and the inhibitory currents tries to push it to some point down here. Okay, so these are kind of physiologically known values. These models have been used a lot and studied a lot. I'm not making anything up, just copying it from the literature. Okay, so what about this one that tells you how hard you are pushing towards these 2 points is the conductance of the neuron. And the conductance basically is raised a little bit every time you get a spike. So every time, if this is the neuron I'm modeling, every time that neuron receives a spike from an excitatory cell, then this one will go up for a few milliseconds. This quantity will be elevated for a few milliseconds, and then it goes back down. Okay. If it gets an inhibitory spike, then this one goes up, which means that you are pushing it here for a few milliseconds. These things only last for a few milliseconds, and then it disappears. But it's hearing from so many neurons, so it's getting like a constant barrages of spikes. So this thing is like oscillating like mad, going up, and this thing is oscillating like mad and pulling the neurons. So the membrane potential is kind of jerking every way. When it reaches here, it fires a spike. That's the whole story that I need to know. Okay, so here's an interim summary: is that so what I've described to you is a dynamical system. Retina is in between that I skipped over. This dynamical system has 2 components. There is a 2D network of LGN. It's actually not network because the neurons are not connected to each other. They're all connected to some other things. They're related via some other things, but they're not connected directly to each other. So we're going to ignore that. So this is just a bunch of neurons here. And then they project to V1 via this coordinate system that kind of really maps the retinotopic map that continues to be extended to here and to here. But the neurons are very different. Here on the LGN, the neurons individually just tells changes in luminance, light to dark, dark to light. This is what they do. These are integrate and fire, meaning they sum the currents that they get, positive and negative. They look at the net current. When it gets high enough, they fire a spike, and then they talk to each other this way. So this is the dynamical system, kind of two networks. So this is a driven dynamical system. You drive it with visual input, but the input is driven to LGN, and that LGN drives V1, and V1 is the part that we're interested in, right? But they made up of very different components. This one only sees light to dark, dark to light. This one adds up all the excitatory, inhibitory, and then fires when it's sufficiently positive. Okay, so this is it, the dynamical system. Okay, so I'm going to getting to orientation selectivity. So here's a neural fact, is that nearly all V1 neurons have an orientation preference, by which I mean the following. So you present some bars to the neuron, when depending on the direction that the angle, the orientation of the bar, the neuron may respond a lot. So this neuron really likes this angle. These two, it's still kind of more or less like. These, it really doesn't like, and the rest it likes even less. Okay, that's what's meant by orientation preference. So every neuron has a preference. It just likes some things and doesn't like other things. And this is what is called a tuning curve, that it's been supposed it likes 0, then it fires a lot like that. And then when you change the angle to the side, it fires less and less. And when you move sufficiently far away, it doesn't fire at all. Okay. So this is the property called orientation selectivity. And is another fact is that nearby neurons, neurons with like orientation, so for neurons with like receptive fields and like orientation preferences, they tend to be bunched together in small groups. So this is a real imaging, actually, of optical imaging of real cortex. You can find a zillion of pictures like this on the internet. Okay, each color represents a region that has a similar receptive field and similar orientation preference. So this is real. Okay, this is also kind of real. Okay. So these are some 2 neural facts. So I said LGN has no orientation preference because it only sees this light. You can put a bar in whichever direction, it's going to see exactly the same thing. And so the question is, how do cortical cells acquire their OS? And so human weasel, who are really giants in the field, I actually attended Weasel's 100th birthday conference just a couple of months ago. It's really amazing, right? He's 100 years old. He's at Rockefeller and he's still working. So so they discovered in the 1960s, these are kind of Nobel Prize winners and so on, right? They're giants in the field of visual neuroscience, the physiologists. Okay? So in the 1960s, they kind of already discovered these things that I was telling you, and they found that a majority of V1 neurons, not all of them, but like 2/3 of them, okay, their receptive fields have a particular structure. It looks like this. So if the neuron is sensitive to this region, it's not sensitive to exactly the same things. There's like a part that's sensitive to changes from dark to light, and a part that's sensitive to changes from light to dark. It comes in 2 bands, sometimes 3, like that. Okay, so they discovered this thing, and the natural conjecture is that, well, why is it like that? It must be because it's wired to LGN in a particular way. It's wired to a row of, let's say, off cells. That's why it's sensitive to this kind of changes, and it's wired to like this type of receptive field probably comes from a wiring to LGN that's made up of a row of on and a row of here off and a row of on. Okay, so this is kind of natural guess. And I have heard many times in neuroscience classes and conversations that this is the explanation for orientation selectivity. Okay, but then so I kind of naively went to the LGN dynamics and tried to deduce from LGN dynamics why is it that if a neuron is wired like this, that it would prefer orientations in one direction but not in another. And I had a little trouble deducing that directly until, well, it's not too much, but it wasn't completely immediate for me. So I figured out a few more math details for myself, and I'm going to share that with you. So in the next page, I'm going to explain how exactly, suppose a neuron is wired to 2 rows of LGN cells, one on and one off. Why is it then that that neuron would prefer a direction and not fire when it's the opposite direction? Okay, so this is the mechanism that I kind of convinced myself with is the following. So suppose a V1 cell is wired to a row of off and on LGN cells, like vertically, like that, vertical. Okay. Oh, in visual neuroscience, people like to use as a stimulus drifting grading. So why drifting grading is that, well, one is that you need something that moves, because if something doesn't move, then LGN only detects changes, right? So if you show it a gray background, LGN doesn't see anything. So you need something that moves. But why this it kind of is in some ways one of the simplest spatially periodic and temporally periodic objects, stimulus that one could see. And also your eyes move. So when you look at a vertical edge, okay, like on a wall or something like that, you don't see a vertical edge. Your eyes keep moving like this from side to side, and the drifting grading in some ways resembles a little bit of that. Of course, it doesn't look like that. It's not periodic in any way, but you see something moving. You see a bar moving sideways when you look at a vertical edge. Okay, so these are the type of stimulus that is used. So now when you present the eye with the drifting grading, so let's say it's going from left to right like that, okay, if the distance between these, I said spatial frequency, that's wrong and really should be spatial period. If the spatial period is roughly is commensurate with the distance between an on and off, you can see that there are some moments when the off cells are very happy because it is seeing something that is changing from light to dark, and the on cells are also extremely happy because it's seeing exactly the opposite. Okay, so when both of these are happy together, they fire together. So this is the pooled LGN response from all 6 of these guys. They are happy together, and then you will see a period when they're both unhappy together because it's the opposite. Okay. Anyways, the important thing is they're happy together and unhappy together. They're on and off. So the LGN spikes come this way. Whereas if you do a grading that goes this way, then at any one moment in time, one is happy, the other one is unhappy. So what you see is that the spikes that they produce are much more evenly spread throughout. Okay. And it's a fact, which I will explain in a moment, that if you have the same number of spikes, but if they are all concentrated and then blanks in between, this would elicit a much stronger response in V1 than if they were kind of spread out. Okay? This is a weaker response. So I'll explain that in the lower part of the slide. But first, I want to observe the following. People often think that, rate models are very common in neuroscience. They think that if you receive more input, then you fire more. Okay. So now that's not false, but you have to kind of interpret that a little bit more carefully. But here, if you look at this picture and that picture, the V1 cell receives the same number of LGN spikes, independent of the direction of the orientation of the grading, because it's wired to these 6 cells. Each one of them fires the same independent of grading. So of course the sum total is the same independent of grading. So there is no difference in the total number of spikes per unit time if you look at a long enough stretch of time that the V1 cell is getting, but it's responding strongly to this, but not strongly to this. In other words, it's responding to the pattern, not the number of spikes. Okay. Okay. So this is something that I had to realize before I looked at that. Okay. So why is it that it likes this pattern but not this pattern? It has a lot to do with this leak term. If you look at this leak, so I'm exaggerating here in the picture, the difference is not as big as this, but what happens is that if you keep driving bang, 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 bang like that, like this part, okay, there's no time for it to leak before it reaches threshold. Once it reaches threshold, it spikes, okay? And then it resets and then you drive it up again and it spikes, okay? Whereas if the spikes are farther in between, then it spikes, it pushes it up, and then it leaks all the way down. And then it goes up and then all the way down. Okay, so the pattern is very, very important in causing in producing different responses. Okay, so the response in vertical edge versus horizontal edge really has to do with just these patterns, nothing to do with the number of spikes. Okay? So that's the okay. So this is, we made up these stories. So can we make a model to make it work? Okay, so build a dynamical system model of LGN and V1. Started doing this with these guys. So he's a real neuroscientist, and 2 of us are mathematicians. Started building this model in 2016. Because it's still ongoing. You can never get a model right, so you keep trying to make it right or make it better or something like that. So here's what a model is like. Okay, so this is with 9 hypercolumns. So we think of these regions, each one of these squares, as having the same receptive field. This is really idealization, right? Okay, same receptive field. And then within each square, we divided it into 6 regions corresponding to sometimes we do 4, sometimes we do 6, okay, corresponding to different intended orientation preference, okay, trying to mimic this picture here, okay. Okay, so what does intended orientation preference mean? Is that, well, we are going to follow the prescription of Humo and Wiesel. If it's intended to be vertical, then we wire it to 2 vertical rows of on and off. If it's intended to be like that, then we wire it to 2 rows of on and off that with this angle. Okay, so this is the wiring between the V1 and LGN that I did not talk about when I kind of said it at the beginning. Okay, so that's the wiring, and within V1, this layer called layer 4 of V1, the connection probabilities are as I had told you before, and each neuron is modeled as integrate and fire as I had told you earlier. So this is the whole model. Okay, this is internally. This is what you see. The wiring is dictated by following the prescription of Hubo and Weasel. And well, I underline intended here. It's intended that this part should fire more in response to a horizontal grading, but intended doesn't mean it will necessarily happen in real life, right? In the model, even not in real life, in the model. So moment of truth, you try to run the simulation in the model. And so these pictures are activity maps that are kind of like fMRI or optical imaging, but it's on a neuronal level. And because it's a model, you can do it to any degree of resolution that you would like, right? So actually, these little squares are about 50 neurons. I've already averaged some of them together. They're on the order of 15 neurons, okay? And this is in response to drifting gradings of different orientations. So for example, if you give it 0 means vertical, so if I present a 0 grading, the parts that should be responding are the parts that are down here that I have put in purple for you, because they were wired. I mean, this is what is intended to be responding, right? Are these regions that are wired with a vertical orientation. And the way to read this, that this is the E and the I. So E and I always fire together. And this is a fact in neuroscience, in the real brain, as in the models. So they always go up and down together. And high means this is the color bar. The color bar is that the warmer colors are higher firing. These are less firing. And I firing is much more, about 3 to 4 times more than E firing. These things are all kind of so the model was actually benchmarked with many dozens of experimental data. Okay, and yeah, this more or less works, right? These parts are firing where they should. Okay, and kind of silent in the horizontal parts when they should. Okay, so it kind of more or less works. Try another one. Let's try to go to 45 degrees. Okay, so I go to this is kind of like a key to reading these things, right? There is no 45 degrees. So, but there's 30 and 60. So it should be this bunch that's firing. And indeed, it's this bunch that are firing. Okay. So the model is more or less doing what is intended. So the next one is a little movie, but a movie of what, right? So I want to say this in clear dynamical systems language, what it is a movie of. We have a model of LGN and layer 4, one layer of we have a 2-layer network driven with a periodic forcing, namely the drifting grading, right? So this is a periodically driven dynamical system. LGN, I told you about earlier, the V1 layer is modeled as there are 9 hypercolumns here of 4,000 each, so 36,000 neurons. Each neuron is a small dynamical system governed by an integrated fire equation. So this is a fairly large network driven by a periodic forcing. So when you do that, it settles into some kind of a non-equilibrium steady state. Okay, because of the external drive, right? It's changing with it. And so that's an invariant measure. So how do I look at that invariant measure? Obviously cannot describe an invariant measure in such a high dimensional space. So I look at 2 observables. One is E firing and one is I firing. Okay, so these observables are not per neuron, but already average over little pixels of about 50 neurons each. So what you're describing here is a snapshot of what these 2 observables look like at a fixed point in time. Okay, what the movie is going to show is that I'm going to take an initial condition and vary it, and you will see these variables fluctuate with time, how they vary with time. Okay, and so here is the visual stimulus. It will change from one grading to another. And this is the kind of a real time in milliseconds, 1/10 of a second. And if you want to check to see if the right part is firing, you go down here to see if the part that's intended to fire that will fire. Okay, ready to go? So I've also smoothed out the time, because if I didn't, it's changing so quickly. It just changed, right, to a different grading eliciting a different response. Okay, changing yet. Okay, is the time component has been smoothed out by about like convolution about 20 milliseconds or so. Otherwise, I cannot look at it. It feels like it might give you an epileptic seizure or something like that. It's really flashing away extremely quickly. Okay, and this is when I have average in space, average in time, and you see all this things happening. Kind of, this is how the network actually computes it. And it is not a phenomenological model, it's actually a mechanistic model. So it is trying to mimic how the real brain actually computes it. Okay. So that's the story with orientation selectivity. So going to direction selectivity. Okay. So what is direction selectivity is that so suppose the neuron prefers these two rows of LGN, so it prefers vertical. So direction selectivity means that the gradient can come from this way or can come from that way. And each neuron, if it's direction selective, will strongly prefer one of these directions, but not the other. Okay. And this is the fact that was discovered in the 1960s, also by Hubo and Wiesel. And it's the neural basis of motion perception, as I said at the beginning. Okay. So experimental facts is that LGN doesn't have any of this, but the V1 cells, about half of them have pretty strong direction selectivity. Moreover, for each neuron, and this is important, that it always prefers the same direction. It's not like one time it prefers one time it prefers. If it prefers one, it always prefers one. It's very consistently, and the property is broadband, and you can change the grading in different ways. It will still prefer exactly the same thing. So LGNs have no properties of these kind, but the V1 cells do, and we're looking for a biologically viable explanation, and none was proposed before for primates. So this is kind of the last part of the story that I want to tell. Okay, so the proposed mechanism is about as simple as can be. It says that, okay, each individual LGN cell does not have a direction preference, but if you add their responses together, if you look at all the LGN cells that project to a single V1 cell, if you sum their LGN, sum their response, there's already a directional preference. Okay, so it didn't kind of come out of the blue. The input to the V1 cell already has it. If you count all the LGN cells together. So I'm going to give you a little kind of cheaty mathematical argument for why that is the case, but cheating and then check it with a model. Okay. So first, let me idealize. Instead of two rows of, let's say, three of these, I just have one of these. Okay, the same thing. Okay, and then I'm interested in the sum of the response of this cell and the sum and that cell. Okay, and each one I'm gonna just take that to be the light intensity map convolved with the spatial and temporal kernels. Okay, what so there's some more, right? There's some background stuff and so on. Let me cheat and just ignore that and just think of this as a convolution. The reason I want to take this as a convolution is that it makes life a lot simpler. If you use a sinusoidal signal, such as these drifting gratings are, you convolve it with some kernel, what you get is another sinusoid. So in other words, if you give it a sinusoidal signal, the response is another sinusoid. It's just phase shifted and with a different amplitude. So this way, it makes the situation much more controllable. But in particular, I just have to focus on this phase shift. Okay, so here's the idea. I want to add two sinusoidal responses, and I want to know when they are the biggest. So the obvious answer is when the phases coincide, right? So when the phase difference is 0. Yeah, this is, of course, when you get the maximum response, right? Assuming other things being equal. Like I say, I'm cheating a little bit, but that is the idea. Okay, so what we want to do is to focus on phase differences. Now, there are two gradings. When a grading is going this way, let's say this is the phase difference. And when the grading is going that way, this is the phase difference. So all I have to do is to look at these two quantities and see which one is closer to 0. The one that's closer to 0 is the direction that the neuron will prefer. Okay. All high school math, right? Okay. And another easy fact, which is also high school math, is that if these two kernels, I wrote K of S, but actually there's a K on for on cells and off cells. If they have the two kernels are the same, but opposite in sign, but are the same, then there cannot be any difference. The phase difference have to be the same. And you can look at it this way. If you go this way and that way, you know, everything is upside down, but the phase differences are the same. Okay. So it's very easy to check. So by symmetry, if the kernels, two kernels are the same, then there can be no directional preference. Okay. To sum up, what I've just said is that DS comes from the broken symmetry caused by different time kernels for the on and off cells. And they have the same kernels that cannot be symmetric, so cannot be any DS. So it must come from the broken symmetry between these two. So the question is, what are the biological basis for the broken symmetry? What, right? I can't just make up something. So actually people had more or less known this for a long time. They created different systems of mirrors and complicated gadgets that reproduce this broken symmetry. But the question is, it's not biological. You want a biophysical model. So where did that come from? From the biology. So we found the following two. The first one is kind of it's kind of an obvious one, is that if you look at the retinal circuit, the on signal has to go through some extra loop to causing the on signals to arrive on average a little bit late. Okay, now that is a very clear way to break symmetry. So if this one is delayed, when it comes from this way, it's as though these two are farther apart, right? And when it's coming from this way, it's as though these two are closer. The symmetry is clearly broken. So that's very easy. So it's broken, but it doesn't really produce too much DS direction selectivity when the grading is going fast enough. It's only when it's because it's only a few milliseconds. Okay? So if it takes like 200 milliseconds to go from here to there, a few millisecond difference is not going to make too much difference. So it works sometimes, but doesn't work a lot of times. So you need another one. And sifting through the data, we found the following fact. So this is from data. Notice that in addition to coming a little bit later, the on kernels are not always, but most of the time taller than the off kernels. Okay, so then I decided that that must be the reason, and here is my cheating argument. Okay, it produces a shift in it breaks the symmetry. Okay, so here's my cheating argument, but it can be turned into more or less real one. Is that suppose the on kernel is equal to the off kernel plus this extra positive part. Okay, that's reasonable, right? It's taller, so let's suppose it's plus some positive stuff. If the signal is a sine function, and I told you that LGN is like taking derivatives, so the off kernel, let's say it turns it into something like a cosine, right? Derivative, right? Okay. But when you convolve with the positive part, what you do is that you get another sine function. So you're adding a sine to a cosine, and that causes a phase shift. Okay. And so this is kind of my little pet theory for why you could have direction selectivity. Okay, so it mathematically it produces all that I have argued is that it produces an asymmetry. I didn't tell you which direction it prefers, right? So now I have to address the question which direction it prefers. And here's another kind of high school type of theorem that you can prove, okay, that says that if you add these two things, it really depends on the relation between this distance and the spatial period of the grading. Okay, if you work this out, you will find that it actually switches the preferred direction at these when the relation little d is the distance between the LGN cells and this, right? So for different gradings, it would switch signs. So when little d is in this region, it for this arrangement, it prefers the left, according to the theorem, and from d over 2 to d prefers the right, from d to 3d over 2 prefers left, and so on. It just keeps switching back and forth. But wait a minute, experiment says no switching of preferred direction. Okay, so are we in trouble? So this says mathematically it switches in direction. Okay, there's no question about that. But in experiment show there's no switching in direction. Okay, so and no, fortunately, is not a contradiction for the following reason. Remember that LGN dynamics is, think of it as the convolution of light intensity with spatial and temporal. Now focus on the spatial kernel. So the spatial kernel is, so meaning that what it is that it's averaging whatever light dark is seeing in some little round region like that, okay? And the size of the spatial kernel is roughly proportional to D, this little d, okay? So when the spatial kernel is big, in other words, when little d is compared to the distance between stripes, in the area that you are averaging over like 20 left, right, like dark like that. Even though it moves, you don't see anything. You always think it's gray or close to gray. So as a matter of fact, there is only a fixed range of spatial frequencies that we respond to. Outside of this range, we think it's gray and we don't respond at all. So what happens is that when little d gets past here, you can check that these are the numbers, these are the right numbers. When it gets past here, and the response goes down to almost like background. And it kind of responds a few spikes here, but not much. So saved, no contradiction with reality because of these facts. Okay, so this is what kind of we propose with this somewhat cheaty theory, idealized theory, that if you add up the feed-forward LGN input, there's direction selectivity. Okay. This doesn't mean that there is direction selectivity in the cortical cells, because there's a hell of a lot going on in cortex. So many cells with different kinds of preferences. The intracortical currents could easily swamp everything. So we're going to put it onto a model to prove that it actually can work. The same model that we talked about before. This started with 2016. I said plus ... By 2022, we've added many more phenomena. So I want to say that we have modeled most of the basic phenomena, but of course there's no such thing as most. Okay, but by now this model can do a lot of different things, including this one. So here's what it does. This is a comparison with experimental data. So I need one way to measure DS. So DS can be measured as a quantity, right? It's the firing rate in the preferred direction compared to the firing rate in the opposite direction. Okay, so you take the same grading, give it in two different directions, and you measure the ratio. Okay, 3 is often what people regard as having direction selectivity. One side is firing 3 times more than the other. And this is kind of the picture that's kind of like the high point of this paper. That green is experimental data and black is from the model. Okay, so I wrote CDF, and then last minute I noticed that I actually had it backwards. It's bigger than X. Okay, so smaller than X would have been. So these are the proportion of cells with this ratio less than bigger than something. So for example, 3 is the gold, and it's kind of usually the point that people look at. About 60% of real life cells have direction selectivity index bigger than 3, and we of course try to tune the model so that it has that, and more or less does. Okay, so I'm pretty sure that this is not the whole truth, but hopefully, some truth, even though it's far from the whole truth. Okay, so let me summarize. This is my last page. Okay, so the summary: the brain is a large and complicated dynamical system about which we only have very partial information. And the challenge for dynamicists is to discover the dynamical mechanisms behind these functions. Okay, I've been working with the visual cortex in part because the visual cortex is a good window into the rest of the cerebral cortex, because it's more accessible. It's easy to have experimental data. People have collected a lot of experimental data. Now, a window doesn't mean that the whole cerebral cortex looks like the visual cortex, but there's a fair amount in common. So this is kind of, I see it as like a kind of a window into something about which we don't have access so much so far. And in this talk, so I propose some biology-based mechanisms for 2 basic visual phenomena: orientation selectivity, which is implicated in edge detection, and direction selectivity, tracking moving objects. So this is kind of in the orientation selectivity. One could think of this as mostly, based on what the proposal of Hubo and Wiesel. I added a few more math details. For direction selectivity, there's no proposal before, and nobody knows whether what I told you is true or not true. Is to be verified or refuted by experiments. And that's my story.
Thank you. Just clap for all the audience. So, are there questions, comments? Anyone?
Can I?
Sure.
Yeah, so if I understand correctly, so the idea is that there is some way in which the neuron in LGN are connected to the visual cortex, right? That
that wiring is doing a lot.
Yeah, the wiring, exactly.
Yeah.
But is that there are some experimental data on that, or is just a supposition?
They are pretty good at measuring things that are nearby, and very bad at measuring things that's connected from one region to the next of the brain. Okay? So there's a lot of experimental evidence, but I don't believe that they don't know how to measure exactly how one LGN neuron is connected to the other. So everything is deduced.
It's just
but from a lot of experimental
right?
data. It's a straightforward connection.
It's a straightforward connection.
It's a straightforward connection with nothing in between. You take an LGN neuron, but this is true of any two parts of the brain too. Okay, if you look at the same sheet, they have a lot of things like connection probabilities and all these things. Right? They can even see some of the things now using different kind of fancy techniques. But from one layer to another layer, they just cannot tell exactly what goes to what. Now, but they have techniques that say from this region it goes to that region, roughly, but they cannot say exactly what goes to what, right? So there are lots of experiments done to try to deduce how things must be connected, but the experiments also fall short of deducing anything.
In some sense, yours is a prediction on the way
it's a prediction. The second one is a prediction. The first one depends on who you talk to. A lot of neuroscientists are happy. I see these subregions. I'm done. Okay. Why is it that these subregions necessarily imply that this is how? Okay. To me, there's still something to be verified, but we mathematicians kind of require more, right? to be convinced. but for the second one, there really is no explanation whatsoever, and what I tell you may be totally false, right? But there's no other thing that people have actually made many other proposals. They have been shut down. Like, well, it's because there's a neuron that does this and that, and then people say there are no such neurons. So this is kind of the game. So there are actually quite a few models of direction selectivity don't even pretend to be kind of biophysical. There are no such anatomical structures corresponding to them. They just make up a structure. If I go there and then twist it that way, and I go there, and then people say, well, there's no structures that correspond to this, right? This one, nobody has shut down yet.
But would there be a way to shut it down? I mean, you would
yeah. I'm pretty sure there are ways. Yeah. It's hard to know what the LGN output is, but it's easy to see. But it's maybe not completely easy to shoot it down, because these things are only statistical. I made it sound like it's always going to work this way, but it only actually works this way a majority of the times, right? So yeah, it would be a little bit hard to do that. But so the safe thing to say is that the things that I relied on have been solidly established. The biological facts that I relied on, that I used, have been solidly established. And actually, some time ago, people just never used them. But so this is a different kind of dynamical systems, right?
May I ask a non-mathematical question, if I may? I mean, do you have any reason why, can you offer any reason why it seems that, the cells are sensitive to movement, but not to like a static picture? Would that be, why is it advantageous for human vision?
I don't know. I don't know. But everything has to go through LGN. Okay. So it is really true that if you show we actually so I should actually kind of qualify that by saying that this is one pathway that I'm talking about. There's another pathway that can see static things. Okay. This pathway does not. Okay. The pathway that I'm talking about is very sensitive to it doesn't require a lot of light. It doesn't require a lot of contrast. It doesn't see color, but it's more primitive. It can see things. Okay, so this is one of two pathways. So this pathway, everything goes through LGN, and LGN really does not. It really requires movement. So here's a pretty well-known fact in neuroscience is that if you fix the person's eyes or the monkey's eyes, there are these things that you can wear to fix it so that your eyes cannot move, right? So your eyes move. This is one of the reasons why it's always kind of moving. Okay. So if you fix a person's eye and present the picture, it fades after a little while.
Okay.
You look at it. It's very dramatic. They show the picture in front, and then it kind of fades into the background, becomes more or less gray. Okay, but the fact that our eyes move, that could be one of the reasons.
No,
Would that be an answer to your question?
You would imagine that would be a consequence of that. I mean, since we are
I don't know whether
we need our eyes to do
I don't know which one is chicken and egg. The thing is that our eyes are we constantly trying to put our phobia on the thing that we want to see clearly, but our eyes are inherently unstable, so it drifts away. And then you correct that and move it back and forth, right? I don't mean these big movements like Saccad's. I want to look at a different part of the room. I mean, you think you're staring at Michelangelo's face, and then your eyes are actually kind of going like this because you can't keep. There's no way you can keep it there. So I don't know which one is chicken and egg, but
thank you. Thanks.
Other questions? And then, okay, thanks, Lai-Sang Young.
Yeah.
And
thank you.
I think,
let me stop sharing.
Yeah, and we move, I think, to the next talk. We're a bit late, so.
So how much time do I actually have?
30 minutes.
30. Okay. Oh, thank you. Thank you.
Yeah, you can take the time it was.
Okay. I understand it's well, so people need to leave of course they would do so. Let me see. I'm gonna try to do this from my iPad, so let's see if this works.
But Italians don't eat dinner till later, right?
Oh, much later. I know that. Yeah, but yeah, people have other things besides dinner to do. Right? So let me see. There we go. Okay. Okay. So I should start given the time.
Yeah, let me just thank you for being here. And so Kevin Lin is the next speaker, and he will talk about coarse-grained modeling of the primary visual cortex. Thank you. And
okay, thank you. So first, I'd like to thank the organizers for this opportunity to speak. So I'll talk a little bit about some joint work with Lai-Sang Young with Zhuocheng Xiao, who's at NYU Shanghai, on some of the computational issues that have come up. So let me see. That's my okay. So I have a pointer that works. All right. So so I want to pick up with this picture from Lai-Sang's talk about so the structure of the visual system, and we're I'm mainly going to be talking about modeling this input layer V1. Okay, and so as Lai-Sang showed, so spiking networks, so networks in which you have actually modeled the neurons and track the electrical spikes that they generate, there can replicate a remarkably large number of the known properties of the visual cortex. So, and they're biologically very detailed and very interpretable, and can lead to a lot of insights into dynamical mechanisms. But one of the problems they have is that they're not so scalable. So for example, in the simulations that Lai-Sang showed, time steps usually a small fraction of a millisecond, and we're often interested in phenomena that take place over seconds or longer, and so that's a many orders of magnitude. And compounding that with other issues. So in biology, very often there are unknown parameters. So one of the things we like to do with models is explore the parameter space. And so all of you know about the curse of dimensionality, right? So if I have a big parameter space to explore, that space grow in some sense the complexity grows exponentially the number of dimensions, and all of this limits the scope of these very detailed modelings to small patches of the cortex. And of course, we are also interested in what happens when you study a bigger patch of cortex. If you want to study things like multiple layers interacting with each other, things like that, a detailed spiking neural network model like what Lai-Sang showed simply would be too expensive. And so, what this talk is about is an effort to take coarse graining ideas, so borrowing these coarse graining ideas from statistical physics and trying to apply them to modeling the cortex. And so what we want is to get rough models that run a lot faster. And the goal here is so that we have coarse grain models that are in a certain sense more efficient, and also so that can be used to complement these detailed models. Okay, and of course, when you coarse grain, you lose something. So these are not meant to replace detailed models, but really but they can be very useful alongside the detailed models. And so what I'll talk about is some of the issues that come up in designing these coarse grain models, and then show some experiments that show that if you that these models can be designed in such a way as to efficiently reproduce some of the properties of V1 that Lai-Sang showed earlier. Okay. So here are the questions that I hope to that I'm gonna try to address. Maybe not all of them in the time that I have, but hopefully hit on a couple of the a few of them. And so one is, how do you capture some of the relevant neurobiology? And maybe if there's a way to even exploit the structure of the cortex to try to speed things up. And then I'll say a little bit more about some dynamical issues like scale separation as I go along. So we as you will see, we take a kind of a mean field approach, and as almost by all of you know, justifying mean field very often requires some kind of scale separation argument. All right, so first I want to recall some very familiar ideas from statistical physics. Okay, so this is a model that probably many of you know very well. So I'm going to just trying to make things concrete. Okay. So imagine I have a dynamical system in which I have some kind of domain, and then I have two large reservoirs that are coupled to the ends, and they inject particles at some rate. Okay, so there's some Poisson clock that tells you when particles get injected, and then they have some mean energies, and the particles bounce around, and then they can bounce around through and then exit the system. And then, so if I wanted to know something about the mean steady state energy of the particles at a particular location x, I have scaled the domain to be 0 to 1. So if you open up a physics textbook, what they would tell you to do is to think about the system abstractly as a collection of smaller subsystems. So here I've written this in a 1D way. The way you should connect this to a picture like this is think about these little gaps where the particles might get trapped for a little while before escaping. And so up here in this Lorentz gas picture, it's really more 2D where so for simplicity, here's a kind of a 1D picture, and the main ideas in kind of a mean field treatment of a system like this is that if you want to know something about the mean steady state energy at some location, one of the ingredients is this idea of a energy flux balance. So if I look at one of these cells here abstractly or back in this dynamical picture, the energy going in should balance the energy going out, right? At steady state, energy cannot accumulate. Okay, and so J is my notation for the mean energy flux between cells, and so there should be energy balance and also balance between the what's being pumped into the system by the reservoir and what's coming out. Okay, so that's a and then the second ingredient is this idea of a local equilibrium. And so if whatever is going on inside each of the inside the cells is somehow sufficiently mixing, then the particles kind of forget which way they came in from, and then so they'll exit in a more or less random way. And I wrote approximately equals here because making much more precise mathematical sense of all of this requires much more care that I'm doing. I just want to focus on the big ideas, the big physical ideas here. Okay, so I'm being a little sloppy. Okay, and then so if you put these things together and pretend that all these things are equalities, then what you get is a so in this particular instance, you would get a discrete version of the Laplace equation, and you solve it, and you get the you will get the linear temperature profile that you expect. Okay, and so for neuroscience, what we want to do is to see how far we can push these ideas. Okay, and so this is a picture that Lai-Sang showed earlier. So this is each square here. This is a hypercolumn, and these are the orientation domains. And so the very natural thing to do is to try to find a scale at which subdivide your cortex into small little blocks and it's so that each block is kind of more or less homogeneous and might have a chance of going to some kind of local equilibrium. And then instead of describing the blocks very carefully in terms of the cells and their spikes, we want to replace those by averages. And so in the context of neurosciences, that means the average firing rates of the different types of neurons, so excitatory and inhibitory. Okay, and so here's a picture. The red box here. This is a hypercolumn, and we've divided into 10 by 10 blocks. I'm going to be calling these blocks pixels just because we're in kind of a visual context. That's another natural terminology. Okay, but it's really a block and a little block of a small number of cells. Okay, and so what do we so by analogy with the physics, what we want to focus on, so what are the things that are important? Well, so just like so the thing that's analogous to energy flux is spikes in and spikes out, right? So the cells in the little within the pixel get stimulated, and then they may respond by spiking, and if we're looking for a steady state firing rates, the number of spikes in somehow has to balance the number of the spikes that are elicited with that response. Okay, things here are in the neuroscience context, things are a little bit complicated because I have excitatory and inhibitory cells. That's in some sense the simplest way to classify the cells in our context, and actually, I'm cheating a little bit because in our model, there are actually more different classes. Okay, I can say that at the end if there's anyone interested. But the so we need to keep track of the E to E, E to I, and I to I, and I to E spikes. Right. So I have excitatory spikes coming from outside the pixel, exciting the E cells inside the pixel, and so on. And then what's going to be my output are the firing rates of the E and the I cells inside the pixel that get that I get in response to the stimulus coming into the pixel. Okay, I left out a thing in the slide. Here we're interested in the cortex, and so the sources of the spikes. So one source of spikes is coming from other neurons in the same layer of cortex that I'm interested in, but also I can get inputs from LGN and also feedback from other layers in the cortex. Okay, so I think of all of those things as somehow external, even though some of those things are also cortical. Okay, Okay, so how do we model these? Let me explain. So the inputs into each pixel can be so the philosophy here is everything we see in a network model I replace by averages, right? And so the way we model the inputs, we just count up on average how many cells so I look at the cells in my pixel, I count on average how many cells are giving me inputs. Okay, and so for example, if I'm interested in the number of E cells connecting to E cells within the pixel, I can calculate this way. So I just average over the cortical patch. And this PEE is my notation for the connection probability between two E cells within the cortex, and then I average over the pixel. Okay, and so I get some an average number, and then the way I can estimate the number of spikes that I receive per unit time is I just do a weighted sum across all the other pixels and with their firing rates. And I can do something similar with the other types of connections, I to E, E to I, and I to I. Okay, so that part's relatively straightforward. Okay. Now, and then how do I compute the outputs of pixels? So one of the since I'm assuming that I can find a appropriate scale, so for these pixels, so that they're all sort of the same, I can I just need to have a recipe for calculating a kind of an average response for cells in the pixel, and so the way we do that is we can simulate the leak integram fire neuron model, and so what we do. Sorry, this is a little bit of a mess, but the important thing here is that if I think the number of incoming spikes, so for example, if I focus on the E to E spikes, if the if the other pixels have these given firing rates, then I calculate this number, and then what I do is I realize a Poisson process with that rate, and that gives me a sequence of times, and then I can use that to drive one of these leak integram fire models to estimate a firing rate. And in this way, if you tell me how many spikes are coming in of different type are coming into this pixel of per unit time, then I can conduct a little simulation and to estimate the firing rate that you're going to get as a result. Okay, and one of the things I want to point out is that because of this assumption that I can that all the cells are statistically within the pixel are statistically the same. To compute these averages, I really need to simulate just one leak integram fire neuron for each type, and so that already is a pretty dramatic simplification. I should pause at this point and say that we are mean field ideas have a long history in neuroscience, and so a lot of people have studied mean field models for different purposes, and this is one of the points of departure between what we do and what and a lot of the prior work is that is this use of a numerical simulation to estimate the response of a pixel. A lot of previous work was more interested in qualitative things like understanding various bifurcations or pattern formation phenomena that can happen, and so very often they assume a specific analytical form for the sake of convenience. Okay. But here we really want to be able to track what happens in a network model. Yeah, Lai-Sang wanted to ask something.
Can I interject one comment, which to me is very important, is that how many spikes a neuron fires only has to do with how many inputs it gets and the timing of those inputs. It doesn't care where the input comes from. This is what allows us to simplify our picture by a bit. So a neuron from far away will fire a spike. It counts exactly the same as a neuron nearby. Okay, you care about what type of neuron it comes from. They have different strengths, but that's all that it cares.
Yeah. Thank you. That's a very important thing that I left out. It's the spikes don't come with somehow labels about what generated a spike is a spike in a certain sense. So and that's one of the things that lets us do this. Okay. Okay, I'm going to move on. Okay, so what does this give us? So if you put it all together, we end up with a for the steady state firing rates, a mean field equation of this type. And so the quantities of interest are the firing rates of the cells, firing rates associated to each pixel of cells of different type. And so here we have E and I, and they appear on both the left and the right hand side. And the C's are numbers that we can compute based on what we assume about the connectivity of the cortex. And the phi EI, these are the so this is my notation for that. These are functions that tell me how a pixel responds to spikes that come in. And so we want to find a self-consistent solution to this set of equations. Okay, and so now to the so to do that, we need to do that. We can only do this numerically. So how do we do that? The simplest thing to do is by a kind of a per car iteration, and this leads to a kind of what you can think of as a multi-scale modeling. All right. So thinking about so my terminology is at the macro level. My macro scale model is the collection of pixels and their mean firing rates, and the micro scale model are these integram fire neuron simulations. And so to solve these equations by iteration just means that if you give me some firing rates on the right-hand side, I'm going to compute some firing rates on the left-hand side. And of course, generally, they're not going to be the same. And I'm going to try to iterate and hope that they will converge to something that's self-consistent. Okay, and so to do this means that to go from step n of this to carry out one step of this means that you give me a set of mean firing rates. I need to instantiate these integram fire things and then simulate them to estimate what the firing rate should be updated to, and then I just repeat. Okay, and this is a kind of a multi-scale structure that's very standard in multi-scale simulation and modeling. Sometimes also called equation-free modeling in the literature. Okay, but it's really just kind of going between the two scales iteratively. But this is actually unnecessarily expensive, and one of the reasons is so the main reason is that if you go back to this picture of the cortex that Lai-Sang painted earlier, one of the things that's really remarkable is that the cortex, when you look at the scale of looking at the scale that we're looking at, is actually relatively homogeneous. It's in a certain sense approximately translation invariant, and so and the thing that really distinguishes the variety of response in space and time that we see is really because of the way external stimuli are applied into the cortex. And one of the things that this implies is that these response functions phi really don't depend on what part of the patch I'm looking at. There's really just a single response function. And so rather than recomputing at every step, which is much faster than simulating the spiking network, but still kind of expensive, we can pre-compute this response function once and for all, and tabulate and interpolate from this table, and then bypass having to do this microscopic simulation every step of the way, and then go directly from firing rates to firing rates. Okay. And this pre-computation from the computational point of view is actually very convenient to split things up this way, because the pre-computation I can conduct in parallel, and so I just do it once and I don't have to think about it, and that's a very nice thing to be able to do. Okay. How am I doing on time? I have a few minutes left.
Yeah, you can take up to 10 minutes.
Oh, okay. I think I may be speaking a little fast, but okay. So let me okay, let's continue. Now, if you do what I just described, so do the Picard's iteration, which is the first thing that we did, that actually will not converge. And now a priori, there's no reason why it converge. And in fact, we want to there's actually a conceptual reason why one might expect that it would not converge. And so here's the reason. If you think about the time for the time scales associated with how neurons communicate with each other within pixels and between pixels, those timescales are actually in cortex are actually comparable, and what that means is that there's no real that we cannot really expect any real sharp scale separation at the level of pixels in these models. And remember, if you remember go back to the to this physics picture that I showed, one of the kind of the standard mantra in physics is that, well, the particle somehow somehow bounce around lots of times before moving on, so there's some local equilibrium, and that doesn't okay, gotta find my slide again, sorry. Okay, so that doesn't so in cortical dynamics, that's not we don't actually expect there to be scale separation, so you don't expect the neurons. You don't expect the neurons within the pixel to actually relax to equilibrium fully before spikes arrive from other pixels, and so to make all of this work, we actually have to take a mixture of the current state, so the firing rates at the iteration, and then what my response function predicts. And conceptually, you can think of this as allowing the pixels to partially equilibrate towards some kind of local equilibrium, but not all the way. Okay, so that's sort of how we think about this. And so the iteration scheme looks like this. So you have a step H, and then so at the nth iteration you update the firing rates in this way. And so H equals 1 means you fully locally equilibrate instantaneously, and of 0, of course, just means nothing happens. And then we experimented with different H's and found that they're actually, for a range of H, you can get this iteration to converge. And moreover, they for a range of H's, and reasonable initial conditions, they almost always converge to the same thing. Okay. And so here's a summary of the algorithm. You start with a cortical model that you wish to coerce grain. We actually never run that large, that detailed model. We pre-compute these local response functions by simulating the intergrain fire neurons, and then we solve the mean field equations by this kind of iteration scheme. Okay. So in the time that I have left, I'm going to show you this algorithm in action. So this first slide shows you the iterations. So this is the initial condition. Here I'm showing the E firing rates. There are 4. This is a 4x4 patch of cortex, and with a so theta equals 0, so with a vertical grading. And you can see that, and so what's shown are the E firing rates, and so what you expect is the cells that prefer the vertical grading should fire very vigorously, and the cells that prefer orthogonal grading will fire a lot less. And so after a relatively small number of iterations, you can see that's the kind of firing pattern that you converge to. And then down here is this is the this is showing in a certain metric the distance to the numerical fixed point that's eventually found. And one thing that's very interesting is that this convergence is highly non-monotonic, and so but nevertheless it seems to find that fixed point eventually, and we did quite a bit of numerical.
Sorry, the number for the color, what do they mean? From 0 to 70, from 5 to 43? I mean,
Oh,
these
sorry.
are,
I should. Sorry. My apologies. This is the color map. So these are the firing
yes.
rates.
What
Yeah.
does it mean exactly? I mean, is the firing rate, I don't know, how
it's
do I
the
interpret
these are the firing rate of the excitatory cell. So you see the very red here means 70 spikes a second. The very dark red here.
I see.
And the top and the bottom scales are different because so 70 is really unrealistic, the high firing rate, and this is a transient that the algorithm goes through, and then it eventually converges to something more reasonable.
So you're starting from background, right? So
starting from background, yeah, I
right.
forgot to say that. Yeah.
So there's nothing, and then all of a sudden you switch on the grading, and actually in real life, the neurons also overshoot, and overshooting here. I mean, not pretending that this is real life at all.
I don't know if they overshoot by
actually,
this much though.
Not maybe. Well, actually, it overshoots some, and they overshoot and then calm down, right? So this one does, right? It kind of shoots up from 0 to 70.
Quite a lot,
It's not
yes.
zero. It's really a
Very
few,
yeah.
right? And then it comes down.
But what about the time? Is that realistic, or
No.
the number of iterations that it takes?
No.
This has nothing to do with real time, right? It's a numerical
the time
algorithm.
is fake. Yeah,
It's a coarse-grained mean field algorithm.
Okay,
it's a coarse-grained algorithm. Yeah, I should have said this more carefully at the beginning. I mean, we're really interested in the steady state, and these iterations are part of our algorithm for finding that steady state. But sort of mentally, with the way we think about it, it's just kind of a fake time, all right? So by its time in the algorithm, and it does mimic the dynamics.
Yeah, a little bit.
A little bit because we are capturing the response to input. And we did do a lot of numerical experiments on this. The numerics do suggest that there's a very sizable basin of there's a fixed point with a very sizable basin of attraction, and that this convergence to that fixed point is very robust to perturbations. And so none of these things are sort of a priori things that so it's not like we have a theory that tells us that there should be such a thing, but nevertheless the numerics suggest that this is a very robust algorithm for finding steady state firing rates. And then let me show you the final results slide. So this is very similar to what Lai-Sang showed before. I guess the main difference is I have 4x4 hypercolumns, and we have divided each hypercolumn into 4 intended orientation domains rather than 6. But these are not important changes. Okay, and so what this shows is the response of our coarse grain model to a variety to gratings with different angles. Let's start with this one. Okay, so this is similar to the pictures that I showed before. So 0 degrees means a vertical grading. All the cells. So in this picture, what you expect is all the cells that correspond to that prefer the vertical grading. So these maybe I should do it this way. Oh, sorry. The problem with the tablets. Okay, so so the cells in these domains, you expect to really like that vertical grading, so they fire very vigorously. And the cells in the orthogonal domains that prefer the orthogonal grading don't. Okay, and if you change the grading so that it goes from vertical to horizontal, then the picture flips. Okay. And then in between, as you change the grading angle from 0 to 90 gradually, you interpolate between those pictures, and this is what you expect to see. And then for comparison, here's a picture that we clipped from one of Lai-Sang's papers from the spiking neural model. I think this is a picture for the vertical vertical grading, and so you can see that the mean field obviously doesn't have the kind of natural variability that you would see from a spiking neural model, but it really does capture in the average sense the structure of the response, and we can also compute tuning curves so we can also compute tuning curves for the different at different locations in the orientation domains. Okay. And I think that's all I wanted to say. So the conclusions the multi-scale these coarse grain models really can capture a lot of what we see in more detailed spiking neural models, and they can be arranged in a way so that you get a very efficient algorithm to predict some of these rough average properties. And we think that going forward, this is a very useful tool to complement more detailed biophysical modeling of the type that that Lai-Sang mentioned. So we can use this to probe larger phenomena that involve larger patches of cortex. Okay, and here are a couple of references for anyone who's interested. And thank you for your attention.
Thanks. Are there more questions?
But I didn't understand. But one thing, can you compare somewhat this coarse grain model with the original model? I mean, I understand the original model is too it's
so
impossible to run,
yeah.
but maybe on a smaller scale or something, just to see.
No, on this scale we can compare so this is a scale on which we can still run a detailed model, and so this is an example of the kind of comparison, right? I don't have the figures in the talk, but so this really corresponds to subset of this, and you can so the thing that's
so actually the network one is simulated on a full network with 36,000 neurons.
That's right.
After you have finished simulating, I average on the pixels because I don't know how to show you a picture with 36,000, right? So it's first computed from the network and then average on pixels. So there's a lot of variability for NK. Nothing is even. You saw the thing moving actually, and this is average over a second, and still there's nothing. I mean, the connections are all kind of slightly off. They are done by coin flips. There's nothing that's really constant. So the picture on top that Kevin has circulated, the 0-1, is the mean field version of that.
That's right. Yeah. So this I should So
so it looks
so
pretty
this is
good.
the mean field,
I mean,
and this
I
is
don't
the
know.
Oh, sorry.
It looks pretty good. I mean, just superficially, it looks pretty good. I don't know. I mean, how to compare exactly.
For steady state, they look pretty good.
Yeah.
The question is what happens when you do things that are not in steady state, which the brain never is.
This we don't know, right? So but the and in the paper we compare other angles also. I mean they do look very good. The mean field model is not going to capture the kind of there's a lot of natural variability coming from the fact that the network, the spiking network is random, right? It's a random instance from a distribution, and so we're not going to capture that from a mean field, but that's sort of the whole point.
More questions?
So we don't really know why, by taking this stepping back like this, that this idea of partial equilibration, we don't really know why exactly it works, but it seems to work.
Yeah,
it seems a little bit strange because it is just a convex combination between the two, more or less.
Oh, you imagine that it's actually headed towards equilibration, but you don't go there. You only go a third of the way.
That's right.
But the third, you assume that there's the assumption that you are really headed towards equilibration, but you never made it there. You're only a quarter of the way.
This makes sense, but I mean that it goes just in such this very simple mechanism that you use, right? It seems
it is very simple. Yeah.
But in the billiard type models, it's also pretty simple. Right?
Okay.
Right? I mean, it's not exactly like this. No, this is actually also kind of messy, right? Why does it go there? Why doesn't it do something else first before going to equilibrium? So we don't know why it really works. Actually, we have not found any initial condition that does not converge to it.
Well, Yeah, that's right.
Yeah, it's because sometimes it ran out of our scale, but
it ran out of our
once
scale,
once you put it back into
that's
scale,
right.
it goes there. So
Yeah,
every time
anything that's sort of within reason, and then even a little bit beyond, everything sort of converged.
Actually, we did these stress models, stress
Yeah.
tests that are totally unreasonable. It will
That's
still
also
go
true,
there.
That's also true.
But why? Why does it do that?
That's incredibly robust. A priori, there's no reason to think there's a fixed point that there shouldn't be unique, all these things, but it just is very robust once you start doing it.
This
There are more questions? Okay, then we thank Kevin again.
Thank you.
Thanks a lot.
So thanks to all the speakers today.